Hello everyone, my name is Ron Cox and this is my Capstone 3 Machine Learning Project, Tornado Event Analysis. I would greatly appreciate it if you could hold all questions until the end of the presentation. Thank you. Here's a little bit of background on me. I served 23 years in the Army, initially as an enlisted counterintelligence agent, where I learned to speak the Korean language at the Defense Language Institute. I then transitioned to the Signal Corps as an officer after attending the Officer Candidate School at Fort Benning, Georgia. Signal officers have a multitude of responsibilities. Basically, anything with electricity flowing through it can fall within your sphere of responsibility. But I was lucky enough to have specialized in information technology during most of my career, with plenty of training and certification opportunities while performing jobs ranging from lower level help desk technician all the way to deputy director of the Joint Network Operations Control Center in Afghanistan, where my team was responsible for the Army network throughout Afghanistan. Please note that my LinkedIn profile info is available in the lower left corner of this slide. I'm moving to Bangkok, Thailand after this course, so I'm available for work from anywhere position as a data analyst in a company capable of processing the work visa requirements to allow me to work legally from the country of Thailand, my new chosen home. Climate change has resulted in a significant increase in weather events, both in terms of frequency and destructive power. The federal agency responsible for responding to those events is the Federal Emergency Management Agency, known as FEMA. With the perceived increase in these weather events, it is important that the FEMA Budget Office adequately plan for and adjust projected budgets in the near term. I've been tasked to analyze a subset of weather event data collected since 1950 to create a machine learning model to assist in budget planning with a focus on tornado events as a proof of concept for the agency. I utilize standard data science methods, procedures, and tools to perform my analysis. In the subsequent slides, I'll take you through the OSEMI data science framework that I use to produce the proof of concept machine learning model. I obtained the data from the National Oceanic and Atmospheric Administration website using Python. There was a compressed file for each year's worth of storm events, a total of 73 files from 1950 to 2022. These files had to be downloaded and compiled into a single data frame, which contained approximately 1.7 million rows of data in 51 columns. I scrubbed the data in Python and Power Query. The initial work in Python reduced the dataset down to relevant tornado events from 1950 to 2022, which resulted in a data profile of approximately 55,000 rows in 12 columns. I used Power BI Desktop to conduct my exploratory data analysis. I first modeled the dataset in Power Query, developed a few DAX measures to support my analysis, and finally selected some appropriate visuals to include a couple of built-in artificial intelligence visuals to determine if my dataset was appropriate for more advanced machine learning techniques. Let's take a look at the Power BI report to see the results of the exploratory data analysis. The dataset in Power BI includes tornado-related data recorded by the government between 1950 and early 2022. The key metrics are displayed in the upper left section of the report page. To the right are two donut visuals that break out total tornadoes by time of day and by season of the year. The line charts in the center show the trends between 1950 and 2022. On the left, the chart highlights increases in all the relevant metrics, while the chart on the right focuses on the tornado count per year with the trend line showing a steady increase. The stacked column chart in the lower left shows the count per year, but enables us to get a sense of the seasonality associated with these events over time. And the last chart is a tree map of the top 5 states with regards to total number of tornadoes recorded. Within the total time period, you can see that there were approximately 55,000 tornadoes between the years 1950 and 2022. The total death count was about 5,424, with 86,000 combined injuries, and a total cost in property and in crops of $61 billion. Almost half of all tornadoes occur in the afternoon hours of the day, and approximately half of all tornadoes occur in the summer months. Here in the center, we can see some peaks and valleys. We see a spike here in 1953, some little spikes, another significant spike in 1965, a bigger spike in 1974, some minor spikes, but the one we're most interested in is in 2011. It's the sharpest increase in most of the metrics associated with tornadoes. You can see in the other chart, it also shows similar trend, but it also highlights, just in terms of count, 2008, but also 2011. So in our case, 2011 is going to be the more interesting year to drill into. So from there, I would highlight that particular year, and you see Alabama has displaced Texas as the state with the most tornadoes in that particular year. I clearly saw some patterns in the data during my exploratory data analysis, so I thought I might have a data set appropriate for machine learning, but I wanted to test that theory before moving forward. Therefore, I used Power BI's built-in artificial intelligence feature to see if it could discern any meaningful insights in the data. I selected the Key Influencers visual, and here you can see that it identified Texas as an anomaly here. So when state is Texas, the average of tornado count increases by 20.11. Tornado count is more likely to increase when the state is Texas than otherwise. Other states were Oklahoma at 7.85 and Kansas at 6.97. And of course, not surprising, after our exploratory data analysis, we see that when time of day is afternoon, the average of tornado count increases by 4.01. And here, the year is more than 2006, so that explains that slight uptick that we saw in the visual on the first page of the report. Since 2006, tornadoes have been increasing at 2.75. So, if we were to drill into the segments here, first segment, Segment 1, the average tornado count is 13.09. This is 5.29 units higher than the overall average of 7.8. And that's when the time of day is afternoon and the year is greater than 2006. Next segment they looked at, also in the afternoon, but this was for years 1970 through 1955. The last segment it was able to identify were the evening hours and the years beyond 2006. And in that particular segment, the average tornado count is 11.38. This is 3.58 units higher than the overall average of 7.8. And this particular experiment told me that I might have a data set appropriate for machine learning. I developed my machine learning model using the automated machine learning feature in the Microsoft Azure Machine Learning Studio. I did, however, have to jump back into Python to conduct some additional transformations to get the dataset ready for machine learning. There was far too much variation in the tornado damage cost column to effectively conduct a meaningful linear regression. Therefore, I categorized the values into 4 potential labels: no damage, low damage, which included any tornado with a damage level below $1 million, medium damage, which included anything above $1 million but below $10 million, and finally, high damage, which includes anything above the $10 million threshold. I interpreted the results in the same tool. Microsoft Azure Machine Learning Studio provides a wide variety of metrics and visuals to assist in assessing the viability of the machine learning models produced in the tool. Let's take a look at the results. I used the Microsoft Azure Machine Learning Studio platform to conduct my machine learning experiment. More specifically, I used its automated machine learning feature. It took about 22 minutes to analyze the dataset, and it suggested, in terms of best model, a standard scalar wrapper XGBoost classifier with a score of 0.88633 for AUC weighted. Let's drill into the details here and get to the explanation. Based on the analysis, the key features within the dataset that had the most impact as far as an aggregated impact were the enhanced Fujita scale of the tornado, the year that a tornado happened, the location in terms of state where it happened, and the length of the tornado. So if we look at the basic metrics for the training set, you can see the standard graphs. Your precision recall, you want to hug this gray line here closer to 1, so we're not quite where we'd like to be, but we are better than a coin flip. So the rock's looking pretty good. You want it to hug this line here, it's not there. Accuracy table, lift curve, calibration curve, cumulative gains. But what we're really wanting to take a look at would be the confusion matrix. You can see it was doing reasonably well on the low damage and the no damage category. We had quite a few misses, but those were the best 2 performing labels as far as prediction goes
and we definitely need some significant improvements with regards to high damage, the damage over $10 million, and in the medium range damage. Perhaps a better format of the data would be more appropriate and get us some better scores in that particular area. Now let's see how the model performed in its test. So we end up with an AUC weighted of 88.5, which is slightly lower than the score we received while training. Let's drill into the metrics here. And the performance looks pretty similar. Let's drill into that confusion matrix. Here we see about the same performance, higher numbers in the training set, but still the performance was pretty good under low damage, tornadoes under $1 million, and no damage, but we still need some improvements in the medium damage range, where damage is greater than $1 million but less than 10 million, and in the high damage, where damage is over $10 million. So the model is not quite yet ready for prime time, but we might be able to tweak it and get some improved performance, perhaps refactoring of some factors, some additional data perhaps, and more importantly, interviews and interactions with some experts in that particular domain, because as a data scientist I may of course be overlooking some key metric that I failed to include in my model. But overall I'm pretty happy with the performance of my first machine learning model.
Although there's obvious improvements that could be made to the machine learning model, I'm pleased with the initial results considering I have no domain expertise in weather events in general or tornadoes more specifically. With regards to preparing for this capstone, my biggest challenge was trying to produce an appropriate problem statement since I don't have relative domain expertise, nor do I have sufficient machine learning experience to determine if the available data is sufficient to solve my artificially produced problem statement. I also wish more time would have been dedicated to factor analysis techniques with some hands-on exercises, as well as time to practice interpreting the results of machine learning models. But I guess that everything turned out better than I anticipated. Thank goodness for Professor Google and Dr. YouTube. Thank you for your time and consideration. And now it's time for your questions. Thanks again.